In 1900, Lord Kelvin, at the time President of England's Royal Society of Science, is commonly quoted as saying that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. That same year, Max Planck invented the first quantum theory. 5 years later, Einstein published his first paper on relativity. These two pillars of quantum physics and relativity form the basis for all of modern physics, which illustrates just how incredibly wrong that statement was, which would paint Kelvin in a rather poor light, except for the fact that he never actually said it. It's actually a paraphrase of a quote from a guy named Albert Michelson, who you'll meet a little later. So, relativity, what is it? I'll introduce it with a joke. My friend told me she had never heard of Einstein's theory of relativity before today. I said, "It's about time." And that's true, it is about time, but also about space and how time and space are not as universal as they seem to be. In fact, space squishes together and time passes more slowly for objects moving really fast. This is explained by Einstein's special theory of relativity, which is the focus for today. Normally, this is the point where I talk about the ancient Greeks, but this time, the thing that we're going to compare against is a bit more recent. In fact, I taught it to you as scientific truth in the first episode of this podcast. Go back and listen to it. And that thing is Sir Isaac Newton. Newton taught us about how things move, which we know as Newton's laws. Very briefly, Newton said that if you have a mass of stuff and you apply a force to it, its speed will change at a constant rate, or in math terms, force equals mass times acceleration. Easy enough, no time shenanigans involved at all. When things move at ordinary speeds, special relativity and Newtonian physics are identical. They give the exact same answers. But when you start moving really fast, Newton gives the wrong answers, and you have to invoke Einstein. Until recently, we weren't able to get things moving fast enough to really notice the effects of relativity. In fact, Newton's laws were enough for us to send men to the moon. But nowadays, there are a couple of reasons why relativity is important to understand. The first is GPS. Satellites need to have a very accurate clock to be able to tell you your location. If their clocks are off, then your position will be wrong. Since satellites travel at 6,000 miles per hour, neglecting special relativity would put their clocks off by about 4 microseconds every day. And yes, that is a very small amount of time, but it adds up. So you'd better make sure you've taken relativity into account, or your GPS might try to drive you into the river. The second reason is atoms and stuff. If for a certain material you know a lot about how the electrons move around an atom, yes, this is quantum, then you can predict what the material will look like. But the electrons in atoms can get moving really fast enough that Newtonian physics no longer works well. One example of this is gold. If you just use normal quantum chemistry, you predict that gold looks silvery like all the other metals. However, if you add in special relativity and it becomes relativistic quantum chemistry, then the gold looks gold like it's supposed to. Neat. And I dare you to try to use the phrase relativistic quantum chemistry in a conversation. Okay, so that's two reasons why you want to understand relativity. But I think the bigger reason is just because relativity is our best description of how reality works, and it's really cool, and it will blow your mind when you learn more about it. Isn't that enough of a reason? Now, before we go on to the juicy stuff, we need to get some preliminary concepts squared away. First, we'll define some terms you need to become very familiar with. Then, we'll talk about two principles that Einstein used to derive his theory. Then we'll talk about what the theory tells us about time and space. So, the terms. First, position. Position is where something is. The Earth's position at the time of this recording happens to be 94.5 million miles from the position of the Sun. The Sun is 152 quadrillion miles from the center of the Milky Way galaxy, or if you're British, 152 billiard miles. They take their billiards seriously over there. Second, speed. Speed is how fast the position is changing. There's also a related term, velocity. Velocity is how fast the position is changing and in which direction. So saying I was driving 100 miles an hour is not a velocity, that's just a speed. but saying I was traveling east at 100 miles an hour pursued by the police car is a velocity because it has a direction. Third of all is acceleration, or how fast the velocity is changing. If your car takes 3 seconds to go from 0 miles per hour to 100 miles per hour, then your average acceleration is 100 divided by 3, or 33 miles per hour per second. It also means you have a really fast car. Another thing to realize is that turning also counts as acceleration. You may have noticed that I defined acceleration as how fast the velocity, not the speed, is changing. I did that way on purpose. Remember that velocity is the speed in a certain direction. So if you change the direction you're moving, then you change velocity, or in other words, you accelerate. As a side note, you can also define words for how fast the acceleration is changing and how fast that new term is changing and so on. These are called jerk, snap, crackle, and pop. And then we run out of names because no one cares after that. So, position, velocity, acceleration. You got it? We good? And the last term you need for understanding relativity is the idea of a reference frame. A reference frame is the background or point of view that you use to determine your positions and velocities and stuff. For example, imagine you're driving a car on the highway, and inside the car, you toss a ball up and then catch it. To you, it seems like the ball went straight up and then straight down. But to the cop sitting on the side of the road with his radar gun, the ball was traveling sideways at 100 miles an hour along with the car you're riding in. So is the ball traveling at 100 miles an hour or isn't it? It depends on your frame of reference. From the car's reference frame, or a coordinate system that moves with the car, the ball just goes up and down. From the police officer's reference frame, the ball is going up and down, but also sideways at 100 miles per hour with your car. Both are correct. So when you get pulled over, you can politely explain to you were only speeding in the officer's frame of reference, but if he had been sitting in the car with you, he would have understood that the car was standing still and it was actually the earth that was moving too fast. That reminds me of a joke. A student is taking the train back to MIT and realizes that Albert Einstein just sat down in the seat next to him. Excitedly, the student asks, "Excuse me, Professor, does Boston stop at this train?" Now we'll talk about the two principles Einstein used to derive his theory of relativity. The first is called the principle of relativity. The principle of relativity is also known as Galilean invariance because Galileo described it 388 years ago, so it's old. The principle of relativity says that physics should be the same in any reference frame. Physics doesn't care if you look at it sideways. It's the same whether you walk into a post or if the post walks into you. The implication is that it should be just as valid to say that the sun goes around the earth as it is to say that the earth goes around the sun. Sorry, Copernicus. The laws of physics should work either way. But doing that leads to some really hard math, so we make some restrictions so that we can use easier math to describe things. And one of the restrictions we make is that we only talk about reference frames that are not accelerating. These are called inertial reference frames. Remember that term. So a car traveling at a constant speed is an inertial reference frame, but a car that is speeding up, slowing down, or turning is not. The Earth has to turn to orbit the sun. So a reference frame where the Earth is still and the sun orbits around the Earth is not inertial and is much harder to work with, so we don't. You're welcome, Copernicus. In relativity, an inertial reference frame is important because it means that you don't have to deal with the nasty math of general relativity, and you can use the much simpler case of special relativity. The rest of the discussion today will focus only on special relativity. Just remember that for special relativity to work, you have to pick a reference frame that is not accelerating, and if you don't, you'll get tricked. In fact, I'm going to trick you a little later, so be prepared. The last piece we need is the constancy of the speed of light. A very smart man named J.C. Maxwell discovered that light is actually a wave of electricity and magnetism. This is a very profound statement that deserves an entire episode of its own, and I promise I'll make that happen eventually, but this discovery also has an important consequence for a discussion of relativity. Maxwell showed that light does not travel instantaneously, but it actually moves at a constant speed of 300 million meters per second. But that raises the question, 300 million meters per second with respect to what reference frame? His discovery implied one of two things. Either number one, that there existed a sort of fixed universal reference frame that provided a medium for light to travel through, which would mean that they would have to throw out the principle of relativity. Or, number two, that light traveled at a constant speed in any reference frame because of weird time shenanigans. But no one had actually realized that weird time shenanigans were even a possibility, so they went with the first hypothesis and named the medium the luminiferous ether. So, two men named Michelson, the guy from the intro, and Morley tried their best to measure this hypothetical ether, this universal reference frame. I won't bore you with the details, but in the basement of a university in Ohio, they tried their best to measure the ether. And what did they find? Nothing. Their experiment came back negative. In fact, it would later be called the most famous failed experiment in history. The reason was this: the ether doesn't exist. There is no such thing as a fixed universal reference frame. Light doesn't have a medium that it travels through at all. And for Einstein, this had implications. Einstein took two things as gospel truth. First, physics does not depend on your reference frame, and second, the speed of light is constant. And from there, he reasoned out the entire special theory of relativity. I will now try to present it to you as best I can. So close your eyes and listen real close. Imagine you're standing on the ground next to a moving train with a bow and arrow in your hand. You shoot an arrow, and then you whip out your radar gun and it measures the arrow at a speed of 20 meters per second. Your buddy is standing on the train traveling forward at 10 meters per second, and he shoots his arrow at 20 meters per second. Homework question 1. What speed does your radar gun measure when you point it at your friend's arrow? The answer is 30. You add the speed of the train to the speed of the arrow to get the total speed. 10 plus 20 is 30. That's basic Newton. But now, replace the bow and arrow with a flashlight. You shine your flashlight, and the light travels at the speed of light, 300 million meters per second. Your friend shines his flashlight. Now here's the important part. What speed do you measure the light from his flashlight at? Is it 300 million plus the 10 meters per second from the train? Does being on the train make his light move faster than yours, like it did the arrow? Maxwell says no, light travels at a constant speed, and you can't make it go faster or slower, no matter what you do. Newton disagrees with this, but it turns out that Newton is wrong. So Einstein reasoned like this. He had constructed the problem so the distance from where the light was released to where it was measured was the same in both situations. Maxwell was adamant that the speed was the same in both situations. Speed equals distance divided by time. If the speed and distance were constant, then time must be passing differently for the two observers. Wait, isn't that kind of drastic? Wouldn't it be easier to just say that light doesn't always travel at a constant speed? Nope. It would break too many things to do that. The other option, a luminiferous ether, had already been disproved by Michelson and Morley, like I mentioned earlier. Einstein was crazy enough to accept the idea that time could pass at different rates for different people. He accepted it, developed his theory based on the idea, and used it to make some wild predictions. And those predictions all came true. Here are 3 of the consequences of special relativity: time dilation, length contraction, and gravity having a speed limit. So the first one, time dilation. Time passes more slowly for someone moving really fast. It sounds like science fiction, and the reason for that is that science fiction authors like to use it in their novels. But it also happens in the real world. We've tested it with planes flying around the Earth. It went kind of like this. We took 2 very precise clocks, put one of them on a plane and flew it around the Earth moving eastward in the direction of the Earth's rotation, while we left the other one on the ground. Looking at both of the clocks from an inertial reference frame, the one on the plane was moving faster, which meant time should move slower for it. and when they compared the clocks, the one in the plane had in fact lost 59 nanoseconds during the trip. It's true, time does pass more slowly when you're going really fast. At only jet speeds, it's not noticeable unless you have a really good clock, but it's still real. This has implications for astronauts too. Astronaut Scott Kelly was aboard the International Space Station for 1 year, orbiting around the Earth at a speed of 17,000 miles per hour the entire time. The thing about Scott was that he had a twin back on Earth, named Mark Kelly. When Scott set out, he was 6 minutes younger than Mark. When he came back, due to the effects of special relativity, Scott was 6 minutes and 5 milliseconds younger than Mark. Okay, that's still a really small amount of time. Something moving faster and for a longer time would actually have a noticeable effect due to time dilation. In the sequels to the book Ender's Game, Ender gets on a spaceship and flies to distant stars at speeds much faster than we can currently make. In the book Speaker for the Dead, 3,000 years have passed for the outside world, while Ender is only about 30 years older than he was in book 1. And this is totally plausible. Getting on a really fast spaceship is like getting on a time machine, except it's only one way. It will take you to the future, but there is absolutely no way to get back to the past. You can time travel using special relativity. All you have to do is get in a spaceship moving really fast, but it's a one-way trip to the future. Since I brought up science fiction, you might also expect me to mention the movie Interstellar. That movie is entirely based on weird relativity time shenanigans. However, most of that is due to gravity, which is described by the general relativity, and which I'm saving for another day. But it's generally the same idea. Time can pass differently for different people under extreme conditions. Now, this all leads to an interesting situation. It's called the twin paradox. Go back to our astronaut friend from NASA. Let's just pretend history happened a little differently. Scott and Mark are twins, but Mark stays on Earth and watches as Scott gets on a spaceship to colonize another planet. But then, halfway through, the mission gets aborted, the ship turns around, and Spaceship Twin comes back. Because of time dilation, Spaceship Twin is significantly younger than Earth Twin. This leads to an awkward reunion. But here's where the apparent paradox comes in. From the principle of relativity, you should be able to imagine the scenario differently and take the reference frame of Spaceship Twin. From his point of view, he stands still while the Earth with Earth Twin on it travels away from him. Then, after the ship turns around, he stands still as the Earth with Earth Twin moves towards him. So, from that reference frame, shouldn't Earth Twin be the one who experiences the time dilation and ends up younger? So which twin is older when they meet up again? Do they each think the other one is older? That can't be right. It smells like a paradox. And the answer to the paradox is that I tricked you. I used a non-inertial reference frame. For most of this trip, if Spaceship Twin is traveling at a constant velocity, then he's allowed to think that his brother on Earth is younger than him. Which brother is younger actually does depend on your reference frame, which is wild. But when the spaceship turns around, it has to accelerate quite a bit to get moving back towards Earth. During that period, the spaceship is no longer an inertial reference frame. That means you can't use special relativity. If you want to take Spaceship Twin's reference frame, you have to use the full glory of general relativity to get the right answer, and if you do that, you'll find that Spaceship Twin is still the younger twin, no paradox at all. The twin paradox teaches us to choose our reference frame carefully, and if we do that, the paradox disappears. Another implication of this is that you can't really use special relativity to age faster than the rest of the Earth, only slower. There's no way to use special relativity to gain a few extra hours to study for your test. Nope, doesn't work like that. To make time pass more quickly for the rest of the world, you would have to accelerate the rest of the world relative to your reference frame. That is, you would have to put the entire planet Earth in a spaceship and send it flying off at high speeds. Since that's not likely to happen, you'll just have to accept that relativity is a one-way trip. One-way time travel. You could use it to speed through a boring week, but you can't use it to grab a few extra hours to nap. So that's it for time dilation. But time is not the only thing that gets messed up. Distance is also relative. It's called length contraction, and it can make you shorter. If you're sitting still on Earth and watch a spaceship move really fast, it will look slightly shorter in the direction it's traveling in. That's not quite right. I should say that it will be slightly shorter in the direction it's traveling in. That's length contraction. But to the guy on the spaceship feels the normal size, and you will appear shorter. That's not quite right. You will be shorter in his reference frame. That's the glory of relativity on full display. Measurements are different depending on your reference frame. Each observer sees the other one as shorter than they would be at rest, and both observers are correct. From my reference frame, I measure 5'11" 3/4 inches. But to a reference frame moving at a speed of 87% the speed of light vertically to me, I'm only 3 feet tall. Sadly, in the way we're talking about it, length only contracts and never elongates, so there is no reference frame in which I gain the last quarter of an inch and reach a full 6 feet tall. Sad mark noises. For the purpose of completeness, I have to confess that I lied to you a minute ago. I told you that a spaceship moving really fast will look shorter in the direction it's traveling in. It turns out that's not true. It will be shorter, but how it looks depends on properties of the light that bounces off it, and which will depend on which direction the ship's going. If it's moving away from you, then yes, it will appear shorter. But if it's moving towards you, it will appear longer. If it's moving sideways to you, it will appear the same size as it was originally, but rotated. This has to do with light from different parts of the object reaching you at different times. It's called the Terrell effect. I don't want to walk through it how it works right now, but know that it exists, and you can look it up on your own if you want to learn more. And that's all I have to say about that. Other than time dilation and length contraction, there's a third implication of special relativity that I want to talk about. It has to do with the speed of light. Here's some background. Light takes about 8 minutes to travel from the sun to Earth. This is actually a plot point in a YA novel called So You Want to Be a Wizard. At the climax of the book, an evil monster manages to extinguish the sun. The wizards have a book that tells them how to defeat it, but the book can only be read by moonlight. So since moonlight is just light from the sun that gets reflected, they have 8 minutes of moonlight left before they're out of luck. Do the wizards manage to defeat the monster in time, or is the earth permanently plunged into everlasting darkness? I guess you'll have to read the book to find out. But anyway, if you look out at the stars, you're looking at them as they were when the light was released. The brightest star in the sky is called Sirius, named after the Harry Potter character Sirius Black. And I'm not joking about that, I'm being serious. Okay, I'm totally joking. Sirius is 8.6 light years away, which means that when you look at it, you're looking at it as it was more than 8 years ago. But it gets much better than that. The closest galaxy, Andromeda, is actually visible with the naked eye, and the light from it takes 2.5 million years to get to us. So when you look at it, you're really looking more than 2 million years into the past. But it gets better. The new James Webb telescope can see light from extremely distant galaxies. And by extremely distant, I mean that it takes light 13.7 billion years to reach us. That's almost as long as the universe has existed. So getting back on track, light travels at a constant speed, but according to special relativity, the speed of light is actually a universal speed limit. Nothing can travel faster than it. That includes gravity. Gravity travels at the speed of light, and no faster. This means that if the sun got disappeared by an evil monster, it would take 8 minutes for us to feel its gravity disappear. And until that happened, the Earth would keep orbiting around the non-existent sun. So you'd better hope that the wizards can fix things in time. Well, we're getting to the end. Surprisingly, it's already been over 100 years since Einstein proposed the theory of relativity. It feels like only yesterday. But wait, let me do the calculations. If you were to travel at 99.9999999% the speed of light, 100 years of Earth time would pass, but you'd only feel 1 day older. That's special relativity in a nutshell. Space and time change depending on how fast you're moving. It's not an illusion. That's just how reality works. And if you don't like it, you can take it up with Mr. Einstein. Except he died in 1955, so I guess you'll have to take it up with his relatives. Next time we'll be talking about germs, viruses and bacteria and protists. Oh my. Peace.